Hello and welcome. My name is Tatyana and I'm your machine learning guide for this practicum. So I would like to give an introduction of what machine learning is about and how we're going to use it, and also introduce you to some terminology of it. I'm going to stay seated. I hope it's okay for you guys. And if you have any questions, then just please ask right away, not at the end. Okay, so in our lab, we use machine learning a lot for biology. We have tons of data, biological data being produced nowadays. For example, I took this picture in one of the genome institutes in China. This is a sequencing machine that sequences DNA, and imagine there are hundreds of rows of these machines and they non-stop produce data. And there are several of such sequencing institutes worldwide, so the masses of biological data we have, they're like really huge, and so there is no way to analyze them experimentally, and that's why we use bioinformatics, we use machine learning in order to process this data computationally and extract some knowledge from it. I promised you that I'm going to talk about some of the algorithms. One of the simplest and yet powerful ones is called naive Bayes. You heard about it, right? You heard about it?
No.
No. Okay, it's really cool. So let me give an example. Let's assume you want to know whether a car gets stolen or not. So what do? You ask 10 of your neighbors whether their cars got stolen or not. So you collect the data, you describe each of the car by the color, the brand, the age, and whether it got stolen or not, right? Having this data, you can define a matrix X with 10 samples. These are the 10 samples, okay? And then you can have a vector Y with the class labels yes or no. And so you know which cars is a yes and which car is a no. Okay, now in order to compute whether a new car, your car will get stolen, you can compute naive Bayes, and this is done with the Bayes rule. So you have your sample vectors, your 10 cars, you have your class labels, yes or no, and then you want to compute this posterior probability, whether your new car will get stolen. So what you have this prior, this is how often you see yes or no in your data set, and in my example that's 50%. And then there is this evidence probability. We don't care about it because it will cancel out later anyways. And the only interesting part is this likelihood probability. And this tells you what is the probability of seeing a sample X given the probability Y. Yeah, we computed by making a naive assumption that everything, all features that describe X, they are independent from each other, meaning that the color of the car does not depend on the age of the car, and so on. So they are independent. And by making this naive assumption, we can multiply these individual probabilities of a car being green and get stolen, of a car being black and get stolen, of a car being old and get stolen. So we multiply these probabilities, and the multiplication makes this likelihood. So really simple. Yeah. Then we have the classifier, and the classifier uses the decision rule, and the decision rule simply picks the most probable class. So this is our likelihood, this is our prior, and this is our max function simply picks the maximum of yes or no. And that's all. This is what the classifier is about.
In the max Ymax?
This is the class label, the maximal one with the maximum probability. So you would get probabilities for yes or no, and the one that is maximum, this is your Ymax. This is the one that classifier chooses. Okay. Yeah? Okay, so back to my example. We want to know whether I am Russian, that's why my car is a Lada. So I want to know whether a black Lada that is new will get stolen or not. So first we calculate this prior, which is 0.5, because we have 5 yes and 5 no's. Okay. Then we estimate, okay, what is the probability of a black car to get stolen? Okay, we look at how many yes we have. We have 2 out of 5. That's the probability. The same for no. It's also 2 out of 5. For a Lada, we count how many Ladas get stolen. Again 2 out of 5. The same we do for no. Okay, then we look at how many new cars do get stolen.
Shouldn't for the black be 2 out of 4? Why is it 2 out of 5?
Black.
Do you also take in consideration the last one that it's not decided?
Okay, let's see. Black. This is this, right?
Yeah.
Okay. Black. These are black. These are all yes. So we have 5 yeses,
But
and 2 of them are for black.
okay, I see. So the 5 mean how many cars are stolen. Okay.
So 5. This is how many yeses we have.
Okay, I see.
Yeah. So everything clear so far.
Yeah.
All right. So we multiply these values. We multiply them with the prior, and then we get this result for a yes, a black Lada to be stolen, and for a no, for a black Lada new. And then we look, which one is the maximum? And this is this one, so the answer is yes, it will get stolen. Okay, we do the same exercise for a green BMW that is new. In my example, if you calculate it, it will get stolen. However, if you have a Lada, a green Lada, it doesn't matter. It doesn't matter whether it's new or old, it will not get stolen. So, the math is clear.
Yeah.
Awesome. Okay, now support vector machines. This is a slightly different classification problem. They were introduced by Vladimir Vapnik in 1995. They became immediately extremely popular. This is a really powerful classifier. In biology, we use it a lot. This is our lab rabbit. It's being used seriously on everyday basis. Okay, so what we have here now, let's assume we have still our cars. We have now 2 values, age and price. Here are old, cheap cars. They don't get stolen. Here are expensive new cars. They do get stolen. Now we have, this is our training data. Okay, this is our observations. Now we have a new car and we want to know whether it will get stolen or not. So one way to do that, we can just look at the nearest neighbor, and this will be a different classifier. Or we can set a line so that everything below the line belongs to one class, everything above the line belongs to a different class. This is actually what support vector machine is about drawing these lines. However, there can be many different solutions, and which one is correct? Right? So what do you think, which one is correct? Which one of these 3 lines is correct? Guess.
It's a middle line?
The middle line?
Yeah.
And what do you say?
I don't know, just go with the first line.
Okay, the correct answer is that is the line with the maximum margin, and this is the distance to both classes. And this line is called hyperplane. Yeah? So in my example, I have a 2-dimensional space, so this hyperplane, this is just a straight line. But if the space would be 3-dimensional, then this would be like a real hyperplane. Imagine this would be like, this would be a hyperplane, so that, so that some instance would be here, and the other instance this would be here.
So it has to be like the same distance from...
The maximum possible, yeah.
Okay, okay.
The maximum possible to instances of both classes. Okay, back to math.
The plane should be at maximum distance to one of the set, right? It cannot be at maximum distance to both of the set.
I think you have to find like a certain point where this is the maximum you can get from both of those plane sets.
From both of the planes.
Yeah.
Well,
because if you have this line, it's maximum on this side, but it's not minimum, and then you can like find a certain plane that is maximum from both of them.
Exactly.
So it mostly it will be at the center of the distance of between those two. Because
It's you find your distance, and then the hyperplane goes through the middle of this.
Okay.
So. All right, back to the math because we like it so much. We have our sample vectors, xi's. We have our class labels -1 and +1. Okay, now the separating hyperplane is given through this vector w, and this vector w gives the orientation of the hyperplane. If you move this vector, then the whole hyperplane is going to move. Okay? Now, if you multiply this w with each of these vectors, with one of these vectors, then the outcome would be either large or equal 1 for these instances, or it would be smaller or equal 1 for these distances. Yeah? Okay, very often the hyperplane does not go through the center, through the starting point, through the origin of the coordinate system, and that's why we have to define this variable b, and this is this how do you call it? This distance from the origin. Let's call it like this. Okay, so you introduce it, and now with this variable b, this whole solution is valid for any data and any hyperplane. Okay, you can combine this two into a single solution where you multiply this by +1 or -1, and then it will be valid seriously for all your data points, for all your samples in the data. This formula. Okay, very often what happens, and actually it happens all the time with no exceptions, when you work with real data, is that the data is dirty. It's not that it's really dirty, it's that there are always some kind of outliers, some points that are either in the margin of the hyperplane or even worse on the other side of the hyperplane. This happens always, believe me. So, so we don't want to change the hyperplane because for the other data it does the separation really well, but we still want to consider these two outliers, like in my example. So what we do, we introduce a slack variable called xi, and this is the, come on in. You are for the machine learning?
No.
No. You have a meeting?
Huh?
You have a meeting here?
Can I talk to you afterwards?
Yes.
It's for the registration for the exam that I missed.
Ah, okay.
I need a signature for...
Great.
Yeah.
Don't miss registrations, ever.
I learned. Can I talk to you afterwards?
Yeah, but it will take time, another half an hour at least.
Oh, okay. That's fine.
Okay, sorry. Okay, so we have this slack variables xi, and they penalize our errors. So the support vector machine always tries to find an optimum between the width of the hyperplane, and so it wants it to be always as large as possible, and between the slack variables, between the penalty, because the penalty should be as small as possible. And this is the optimization problem. It can be expressed by formulas, and it's not very hard to do so, but for now, for this scope, I decided that I will call it a miracle, this optimization problem. So the outcome of this miracle is a quadratic function, this one, where we have our class labels, we have our samples, we have our b, this is the distance from the origin, we have our test sample, then we also have this alphas. And for most samples, alphas would be 0, and for those for which alphas are not 0, they are called support vectors, and these are those samples that sit on the margin and they define the hyperplane. So the hyperplane is always the distance to the support vectors. Okay, so support vector machine does not need anything else but the support vectors in order to set the hyperplane. Exactly, and the outcome of the decision function is the distance to the hyperplane. The closer to the margin, the less reliable the support vector machine is, that the prediction is correct. The wider, the more the distance, the more is the distance, then the more sure support vector machine is that the prediction is correct.
Okay, so the more big it is, the more...
the more certain.
Okay.
Yeah. Any questions? Simple. All right, so that was the theory that we need to know so far for our classification. I want you to give just a feeling of how it's being used for ourselves. We have not done any predictions on Pokemon data, so this we have not done. So for us it will be a learning experience as well, but we are experts with biological data. So I myself, I am an expert in predicting protein localization. These are cells, and in colored are proteins that are localized to different compartments of a cell. So you can either determine a localization of a protein using fluorescence methods like shown here, but all experimental methods, they cost money, they take time, they're not very accurate, and they're not very complete. For example, yeast, this is an organism for which people study localization for at least 2 decades, and still like 1/3 of it is localized experimentally. So imagine that for human this number is so much smaller. So our aim, and also the aim of this group, is to develop computational methods that, given a protein sequence, it runs through a predictor, our machine learning classifier, and then it outputs where in the cell it's localized. So actually there are some principles of how proteins being transported to different localizations. As a matter of fact, there was even a Nobel Prize given for this discovery that these principles exist, and their work as follows: is that if this is a protein, this is RNA, this is a ribosome that translates the RNA into protein, transcribes the RNA into protein. The protein sequence will have a signal peptide. It's being recognized and being pushed to a pore in an organelle called endoplasmatic reticulum. It's being pushed. Once it's there, it's being cleaved, and then once it's being cleaved, the whole protein gets into this compartment, and then from here, this is the mature, the final protein is being transported out of the cell. So there is a strict principle of how it works, and if you take the sequences of the signal peptides of these guys here and put them one above each other, then you will see something like this. We will see that some amino acids, they are more often occurring than the others, so the rule is like really there. And so these are the pioneers who started developing machine learning methods for this kind of problems. They developed, for example, this method. They used exactly this observation for their prediction. So imagine we have our amino acid sequences, and now this is our training data. And now we know, okay, so these guys, they do have a signal peptide, and these guys, they don't have a signal peptide. Okay, now we want to feed this information in a support vector machine. How do we do it? Right? So here we have protein sequences, but support vector machine works with vectors, as we saw before. So how does this transformation done? Any ideas? So how do you put anything in a support vector, or in a vector? Anything. For example, be it email data. How do you transform an email to a vector for classification? Like binary? Yeah. For example, yes. For example.
I'm not sure. I just guessed.
And how does your binary vector would look like? What is the rule for the transformation?
I would say, like, guessing from that the ones that are positive will be ones and the ones that are negative will be zeros.
No, these are class labels. This is like this. If this is a vector, then a vector gets a class label +1 or -1. But what is the step from going from here to here? If this would be an email, how would you get from an email to here? Any crazy idea? Now, for example, you could look if a certain word occurs.
Yeah, maybe classify them by the header or the subject.
Exactly.
Yeah.
Exactly. So you look at the header, and then you look for a certain word, and if this word appears, for example, I don't know, whatever it can be, then in your vector you can increase the value for this word by 1. Yeah, this is like a very, very simple, trivial approach. And that's exactly what we do in bioinformatics as well. We look, so altogether there are 20 amino acid. The amino acid, this is one of these letters. Altogether there are 20, and then we count, okay, how many each of the amino acid occurs in my sequence. So the vector has the length of 20. This is the alphabet. And then, for example, for this sequence, we count 1M, we count 3P, we count 1A and 1D. And this is then the input to our machine learning classifier. Clear?
You have a big sequence over there, but
this is just an example. This is just to make it more easier to explain.
Okay. I thought from that you just took this, so I wanted to know why you have taken the MPPAD.
Yeah. Okay. So clear. Everything is super clear. Cool. Okay, so once you define your features, you want to know whether these features would in principle work or not. One way in doing so is to visualize your data. So this is an example of a sample of samples. These are the samples described by 4 attributes. In my previous examples, there were 20. By the way, each of them is called an attribute of a vector. Yeah. Okay, so this is an example of 4 attributes, and we see that combinations of some attributes, they separate the data quite well, but some don't separate so well. So maybe this is a not so good choice to use these attributes. I don't know, but it's definitely a good choice to use these attributes. So this gives you an idea of how your features work. So here it looks fine. We can go on. Another very, very important concept of machine learning, that's called overfitting. So you have your training data set, you train on it, and then you try to train your method such that it can also generalize to some novel data, to test data that it has never seen before. Okay, so if this is number of free parameters, these are, for example, our features or any other parameters of a machine learning method, and this is the performance, from bad to good, right? Okay, so this is our training set, and this is our test set. And so when you develop a classifier, you will see that, okay, you improve your parameters, and then the performance on the test set improves as well. But at some point, the performance of your method will be increasing on your training data, but it will dropping on the test data. Why it will be the case? Because your classifier will learn your training data by heart. It will know everything about the training data, but that's it. It will be optimized for the reality of this, but not for the reality of this. So this would be a very bad classifier. Something like here would be a good classifier. Okay? A rule of thumb to avoid overfitting is to have 10 times as many samples as free parameters. This is a rule of thumb. Okay, so one way of avoiding overfitting is to train your data on some part of your data and test it on the other part. Yeah? However, if we do so,